Welcome to Lecture B5, in which we will talk about the iterative solution of linear systems of equations. We've already talked about two methods for solving a linear system of equations. One was Gauss elimination. In that case, we looked at our linear system of equations, we formed the augmented matrix, and then used the Gaussian elimination procedure on that augmented matrix to find the solution to the system. And the other technique, which was a little bit more involved us finding the inverse of the system matrix using the Gauss-Jordan elimination. And then once we noted that once we had the inverse of the matrix, we could then solve the system for any possible right-hand side by simply performing a matrix multiplication, multiplying the inverse of the matrix times the given right-hand side. But both of these methods do require a fairly large number of calculations in going through the either the Gaussian elimination or the Gauss-Jordan elimination procedure. In this lecture, we'll talk about an alternative method to solve a linear system of equations. And these are iterative solution techniques. And we will discuss a couple of different iterative solution techniques in this lecture. Iterative solution techniques are typically used when there's a large number of unknowns and when the diagonal elements of the matrix, in fact, I say the matrix, but really you don't ever have to really create the matrix. But let's say if you had a system of equations and you did form the matrix, and if it were going to be a sparse matrix, which means that it has mostly zeros, and if it's a large matrix, in other words, this is a large system with many equations and many unknowns, and if the diagonal elements of the matrix tended to be larger than the other elements, well, this is the kind of situation where we would use, and we would typically consider using an iterative solution technique. Now, for the sake of this lecture, of course, it's not very practical for us to try to solve by hand a large system of equations. That would take too long. So for the sake of the examples in this lecture, we'll use small systems of equations. But again, do remember that typically the iterative solution techniques are used with large systems of equations, and also frequently they will be sparse and diagonally dominant. So to illustrate, the first technique that we will discuss here is going to be the Gauss Seidel technique. And as an illustration of the use of this technique, let's look at the following system of equations. So we'll have 2x1 minus x2 equals 2. 2x2 minus x1 minus x3 is equal to negative 2. And 2x3 minus x2 is equal to 34. So clearly, this is a very small system of equations. It's not the kind of situation where you would typically use the Gauss Seidel technique, but we're using it, in this case, we're choosing a small example so that we can do this by hand. Now, the first thing I want to note for you is that we can solve this system of equations directly using Gaussian elimination. Now remember, if you did use Gaussian elimination, you would want to form the augmented matrix, and it would be important for you to reorder these equations so that in each one the first variable is x1, the second one is x2, and the third one is x3. But you could easily do this, and well, maybe it's not even a bad exercise real quickly. So let's just we'll say quick calculation of exact answer. Now again, keep in mind that in practice, we're considering now a large system of equations, so it would not be easy for us to do this exact answer very quickly, and that's why we would want to consider the iterative solution technique in the first place. But in this case, we're so small, we can quickly calculate the exact answer, and that will give us something to compare to when we begin to consider the details of the iterative technique. So the way, just to remind you then, the way that we would calculate the exact answer would be this. As I just said, we want to reorder these equations so that we'll always have x1 first, x2 second, and x3 third. So we would have, for the first equation, we would have that. For the second equation, we would have minus x1 plus 2x2 minus x3 is equal to negative 2. And for the final equation, we'll have 0x1 minus x2 plus 2x3 equals 34. And so now we're ready to form the augmented matrix. We will have 2, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 2, 2, negative 2, 34. And notice that for this matrix over here to the left, on the left part of the augmented matrix, you can see that what we mean by diagonally dominant. You see that the diagonal terms are the largest terms in the matrix. Now this matrix is not one we would typically think of as being very sparse because there's only 2 zeros, but you do see a little bit of the idea. And if we had large system of equations, we would have mostly zeros, with typically the non-zero terms would be crowded typically relatively near the diagonal. But again, the diagonal we're thinking of this as being diagonally dominant, so typically the diagonal terms are the very largest terms in the matrix. Anyway, so this is the matrix we would get, and let's now have a quick review of how we would get the exact solution. So as we've said before, different people would approach this in different ways, but if it were me and I'm solving this by hand, then I like to proceed as follows. I would interchange the first and second rows. That's not necessary at all, but I like to have a 1 in the upper left hand corner. So I'll interchange the first and second rows and I'll also multiply the resulting first row by negative 1. So I'll get 1, 1, negative 2, 1, 2. Now that comes from multiplying the second row by negative 1 and then interchanging the first row and the second row. 2, negative 1, 0, 2. That's just the first row moved down to the second row. And then the final row I'll leave as it is. 0, negative 1, 2, 34. Now I'll add negative 2 times the first row to the second row. So I have 1, negative 2, 1, 2. Negative 2 times 1 is negative 2, and add to 2 is 0. Negative 2 times negative 2 is positive 4, and add that to negative 1, and you get 3. Negative 2 times 1 is negative 2, and 0 gives negative 2. And finally, negative 2 times 2 is negative 4, and 2 is negative 2. And we already have a 0 here, so we don't have to worry about that. We can just write down the last row. And while we're writing it down, I'll go ahead and multiply by -1. So I'll get 1, -2, -34. And now I'm going to interchange, and keep in mind now, you might do different steps in the Gauss elimination procedure, and that's perfectly all right. I'm just doing what's easy for me to do, trying to avoid fractions and do this as simply as possible. So I would have 1, -2, 1, 2, and I'm going to interchange the second and third row. 0, 1, -2, -34, 0, 3, -2, -2. Now I'll multiply the second row by -3 and add it to the final row. So I have 1, -2, 1, 2, 0, 1, -2, -34. When I multiply this 0 by -3, I get 0, and add to 0, I still get 0. When I add this, multiply this 1 by -3 and add to this 3, I'll get 0. When I multiply -2 times -3, I'll get +6, and add down here, 6 minus 2 is 4. And -3 times -34 will be 102, and add that to here, and we just have 100. So now that we've eliminated all the non-zero terms below the main diagonal in the augmented matrix, we write down the corresponding system of equations and use back substitution to finish this solution procedure. So we have x1 minus 2x2 plus x3 is equal to 2. x2 minus 2x3 is equal to -34, and 4x3 is 100. The last equation implies that x3 is equal to 25. So when we plug that into the second equation, we have x2 minus 50 is equal to -34. And if we add +50 to both sides, we get x2 is equal to 16. And then if we plug in these values for x2 and x3 into the first equation, we get x1 minus 32 plus 25 is equal to 2, which is the same thing as saying x1 minus 7 is equal to 2, which means x1 is equal to 9. So our exact solution to this system of equations is x1 equals 9, x2 equals 16, and x3 equals 25. And once again, I want to emphasize, we've calculated this for two reasons. One is for review, and two is for the sake of comparison. But again, in real life, if we're thinking about an iterative solution technique, that means that we're talking about, in practice, we're talking about a large system of equations where it would not have been nearly so easy to get the exact solution. Okay? So now the question is, what is this Gauss Seidel technique, and how would it allow us, what is this alternate way of solving this system of equations? Well, what we do is take the system of equations we're given, and we look at that diagonal term in each equation, and we're going to solve that in terms of the other variables. So for instance, in the first equation, the diagonal term is x1, and the second equation is x2, and the third equation is x3. So if we solve those variables in terms of the others, what we'll get is the following. And the first equation becomes x1 is equal to 2 plus x2 over 2. The second equation will become x2 equals x1 plus x3 minus 2 over 2. And finally, if we look at the third equation, we get x3 is equal to x2 plus 34 over 2. Now, so far, that's been very easy. We've just taken each equation and rearranged the terms in it and solved for the variable corresponding to the diagonal element in terms of all the other variables. So we get these three equations. Now, to do this numerically, what we will do is the following. We're going to have what we will call update equations. Well, actually, maybe let me say this. I'll have old x1 old x2 and old x3, and I'll also have new x1, new x2, and new x3. And it really doesn't matter what I have in new x1, new x2, and new x3 because I'm going to update those in just a moment. But just for the sake of convenience, I'll go ahead and make each one of those 0. Now for old x1, old x2, and old x3, what we have there is our initial guess for the solution to this system of equations. Now, frequently you don't really have any idea at all what x1 and x2 and x3 might be. And in that case, and we'll assume that's the case here, and when you're in that case, the usual thing to do is just to guess 0. But maybe, in some cases, if you're solving a problem, if the system of equations corresponds to some physical problem you know about, and maybe you have a rough idea of what x1 and x2 and x3 are going to turn out to be, then it sometimes can make this procedure a lot faster if you can make an educated first guess. And so if your first guess is fairly accurate, what I'm saying is that you might converge to a more correct answer or a good answer very much more quickly than you would if you started out with a guess of all zeros. But since we don't know anything about this system of equations right now, we don't know where it came from, what it corresponds to, we'll just guess old x1 equals 0, old x2 equals 0, and old x3 equals 0. So far all we've done is to define these old and new versions of each one of the variables. Old x1 and new x1, old x2 and new x2, old x3 and new x3. And now we'll have what we call update equations. And these update equations will allow us to get new values of x1, x2, and x3 from the old values. And they will be based on the equations that we have derived right here. So we have new x1 is equal to 2 plus old x2 over 2. And that comes from the first equation here. And then we'll have new x2 is equal to old x1 plus old x3 minus 2 over 2. And finally, new x3 is equal to old x2 plus 34 divided by 2. So these update equations are based on the three equations we have above, which were themselves derived from our original system of equations. And the idea here is that we start with this initial guess, with some initial guess for the old x's, old x1, old x2, and old x3. And then once we have that initial guess, these update equations will allow us to calculate new values for x1, x2, and x3. Now, once we've calculated those new values for x1, x2, and x3, we can compare them to the old values. If they're very close, we might decide that we're done, and that since there wasn't much change, the solution that we have already, which is just all zeros, is the correct solution. But if there's a significant difference between the new x's and the old x's, then what we will do is update the old x's, make them the same as these new x's that we've just calculated, and then that we have updated the old x's, now we'll update the new x's again. And at each step, we can compare the new x's that we calculate with the old x's, and if there's as long as there's a big change between them, then we'll update the old x's with the new x's that we've just calculated, and then we'll calculate new x's. And we keep doing that until hopefully we finally get to a situation where the new x's and the old x's, where there's not much change anymore, and that situation is referred to as convergence. And then we presumably have this solution to this system of equations. So let's now you can see that even with just 3 variables, this would get tedious in a big hurry, but I do want to show you a few results. Okay? So, and obviously, this is best done with a computer. Okay, so the some preliminary results I'd like to show you are the following. Okay. After let's say after one step here, just to after one step. Okay. Now this is the old x's have not been changed yet, so we still have old x1 equals 0, old x2 equals 0, old x3 equals 0. But at the end of that first step, what are the new x's? Well, new x1 will be equal to 1. New x2 will be equal to -1. And new x3 will be equal to 17. And I think you can see exactly how those values arose. Just plug in for new x1, we plug in 2 plus old x2 is 0, so 2 plus 0 is 2 over 2 is 1. That's how we get 1 for new x1. And then for new x2, we have old x1, which is 0, plus old x3, which is 0, minus 2. So we have minus 2 in the top over 2, and that's how we get negative 1. And then finally for new x3, we have old x2, which is 0, plus 34 is 34 over 2 is 17. So that's how we get these values for the old x's and the new x's at the end of step 1. Now obviously if you compare the new x's with the old x's, there's a big difference between the new x's and old x's. And so therefore, when we notice that, what we're going to do is in the next step, so let's now, after 2 steps, now at the beginning, at the very end of the first step, or maybe you can say the beginning of the second step, is when we will update our old ones. So now, since there was still a big difference between the new ones and the old ones, we'll update the old ones. So we'll have old x1 is equal to 1. Old x2 is equal to negative 1. And old x3 is equal to 17. So once again, now I want to make sure this is clear. There's big differences between our new x's here on this line and our old x's on this line. So therefore, we're going to go again with our iteration, with our update equations. We want to keep on going. We haven't converged yet. So the first thing we do is move these new values that we've just calculated into the old values, and we'll calculate new values. So we set old x1 equal to the new x1 from the previous step, old x2 equal to the new x2 from the previous step, and old x3 equal to the new x3 from the previous step. And now we're ready to calculate the new values again. And this time, what do we get? New x1, new x2, new x3. And what are the values at the end of step 2? At the end of step 2, our values would be 0.5, 8.0, and 16.5. And just to make sure this is all perfectly clear, I think I'll, instead of using the word after, I'll say end of step 1. And here I'll say end of step 2. Now, still you can see that there's big differences here at the end of step 2. Big differences between the new x's and the old x's. Maybe not such a huge difference between new x3 and old x3, but certainly big differences here between new x2 and old x2, and a fairly large difference, at least percentage-wise, between new x1 and old x1. So we would go again. Now, this is going to get tedious if I write down every one of these, so let me skip down just to show you some typical results when you use the Gauss Seidel procedure. Let me show you some values that we would get. So let's jump to end of step 10. What would we have? At the end of step 10, we would have, okay, we're going to have old x1, old x2, old x3, new x1, new x2, new x3. And at the end of step 10, these values will be as follows. We'll have 8.5, 14.9375, and 24.5. those will be the old values at the end of step 10. And the new values will be 8.46, 8.75, 15.5, and 24.46875. And so let's compare now. Well, obviously we have much better agreement between the new x's and the old x's than we did in steps 1 or 2. It looks like there's a relatively small difference between old x1 and new x1. And now the difference between old x2 and new x2 is still relatively large, but quite a small difference between old x3 and new x3. So, you would have to make some judgment here as to whether you want to stop or not. But of course, if you're doing this with a computer, which I think is the only reasonable way to do it, then it certainly doesn't cost you much to go a few more steps and see what happens. And so let's do that. Let's go. I'm going to go ahead and jump down to the end of step 20, and let's see what we have then. Old x1, old x2, old x3, new x1, new x2, new x3, and I'm just in these values, I'm going to show everything that I'm not going to try to be consistent with the number of significant digits. I'm just showing you what the computer printout was. Just trying to get across to you the gist of this method. So after 20 steps, what we would have is the following: 8.984375, 15.966796875, and 24.984375. These are the values, the old values at the end of step 20, and the new values, okay, 8.983398, 4375, 15.98, 4375, and finally 24.98, 3398, 4375. That would be after 20 steps. And you can see that now we do have pretty close agreement on all three of the x's. On the old and new values of x1 are certainly quite close. The old and new values of x2 are quite close, as are the old and new values of x3. So, you would have some convergence criterion to decide when to stop this iteration procedure. And it would typically be something like when the percentage difference between the new value and the old value is less than a certain amount for each one of the variables. It needs to be for all of them, not just for one of them, but for all of them. Then you would quit. And so if we decided to quit here at step 20, then you could see we would take our answers to be these new values for x1, x2, and x3. Now let me remind you that what we found above was that the exact values were x1 equals 9, x2 is equal to 16, and x3 is equal to 25. And so you can see that even though we never solved any matrix equation directly, we never stored a matrix, we never had to fill a matrix, even though we just solved these equations, these updated equations over and over, we have come up with answers that are quite close to the exact answers. And so that shows you how the Gauss Seidel method works. Now, I'd like to discuss one more method before we get to some problems. And this other method is called the Jacobi method. And it is very, very close to the Gauss Seidel method, but it's just a little more, it can be, under some circumstances, it can be more efficient. Now let's look at these updated equations here that we have for the Gauss Seidel method, and I'll copy this and repeat it down here with the Jacobi method. Okay, so there are the update equations that we had before in the Gauss Seidel method. And if you look very closely at this, you might begin to have a question. And the question goes like this. Okay, we first calculate new x1 using the old value of x2. Then we calculate new x2. Now, a question might occur to you. When we calculate new x2, this update equation tells us to use old information, the old value for x1. But presumably, if our answer is getting more and more accurate as we proceed, it seems like it would be more accurate to use this value of x1 that we've just calculated here. Now, for x3, we don't have that option because we haven't calculated a new x3 yet. But for x1, it seems like it'd be smarter to, instead of using this old value, to use the new value that we've already calculated. So we'll have new x1 plus old x3. Let me make this a little clearer. So new x1 plus old x3 minus 2. Now, what about when we calculate new x3? Well, we've just updated our information for x2, and so again, the thinking is that presumably this new value for x2 is more accurate than the old value of x2, so instead of using old value x2 here, we will use new x2. So overall, the philosophy of the Jacobi method is to always use the freshest data we have, or you might say the most recently calculated value. As soon as we update a value of x, then we'll start using that new value rather than continuing to use the old value until the end of that particular iteration that we are on. So let's say that we did this, and let's again do a few calculations and see what we would get. So end of step 1, let's see what we will get here. Give me one moment. Okay, so after end of step 1, we have old x1, old x2, old x3, and I'm assuming that we began with with the same initial guess as before. So the old ones have not been updated yet, so they're still all 0. But what about new x1, new x2, and new x3? Well, these will be 1.0 minus 0.5 and 16.75. And let's just make sure we understand how to calculate this. Okay, so when we calculate new x1, we'll have 2 plus old x2, so that's 2 plus 0 is 2 over 2 is 1. So that's how we calculate this 1. Then for new x2, we will have the new x1, which is the 1 that we just calculated. So 1 plus old x3 is 0, so that's 1 plus 0 is 1, minus 2, so negative 1 over 2. That's how we get the negative 0.5. And then finally for new x3, we'll take this new x2 that we just calculated, minus 0.5, add it to 34, so that'll give us 33.5, and then divide by 2, and we get 16.75. Now, again, there's clearly a big difference between the new values of x and the old values of x. And so we would then store the new values of x into the old values. So we would set old x1 equal to 1, old x2 equal to minus 0.5, old x3 equal to 16.75, and then calculate new values for the new x1, new x2, and new x3. And so when we do that, we'll say end of step 2. So again, old x1, old x2, old x3, new x1, new x2, new x3. And as I just said, in the old ones, we will store the new ones from the previous step. So we have 1.0 minus 0.5 and 16.75. But now the new values for the new ones will be 0.75, 7.75, and 20.875. Now, still, the differences are significant, so let's jump on down as we did before. We'll say end of step 10. Old x1, old x2, old x3, new x1, new x2, new x3, and at the end of step 10, the numbers that we will get are 8.935546, 875, 15.93, 55, 46875, and 24.96777, 34375. The new values are 8.96, 777, 34375, 15.96, 777, 34375, and finally 24.98, 388, 67, 188. And the thing I'd like you to notice now is that notice how close the new values for the x's and the old values of x's are after only 10 steps. If you compare that to what we had before, you see that the differences between the old x's and new x's after 10 steps was much larger when we used the Gauss Seidel procedure than it is now when we use the Jacobi method. And also you see that remember that our exact answers were 9, 16, and 25, and notice how close we already are to 9, 16, and 25 after only 10 steps. We're almost as close after 10 steps of the Jacobi method as we were after 20 steps of the Gauss Seidel method. So this is why the Jacobi method is sometimes preferred to the Gauss Seidel method, because it typically gives more rapid convergence to the answer. Now, there are iterative techniques that converge much more quickly than either one of these methods, but they are more complicated, and so that's why we don't cover those in this class. There are also iterative techniques that are guaranteed to converge under certain situations, though they will be guaranteed to converge in a certain number of steps. But again, this is typically these are more complicated than these very simple methods, Gauss Seidel method or the Jacobi method. But the point of this lecture is just to show you that there is another way frequently. Now, this is not appropriate for all systems, but for some systems of equations, typically the kind of system of equations that you would use when you use a partial differential equation technique, large systems of equations that are sparse matrices, diagonally dominant. In that kind of a situation, an iterative technique can often be very useful. It avoids the problem of having to fill and store a very large matrix, and so this can be a useful thing to know about for sure. So now let's consider some problems related to this idea. So now let's consider the following problems for this lecture. In each of the problems, we will be concerned with this system of equations, which we will want to solve using an iterative technique. And by the way, for the in-class problem, we will still be using this same system of equations. So you might want to go ahead and note it, because it will not be repeated. So you go ahead and write a note to yourself that this is the system of equations that you will be considering for the in-class problem as well. Okay, so here's the system of equations, and the first question is the following. If we use the Gauss Seidel technique, what will be the update equation for new x2? So I'm giving you part of the equation right here. I'll say new x2 is equal to, and then you have to decide what the right-hand side of that equation will be. Is it choice A, old x1 plus old x3 minus 8 over 2? Or choice B, new x1 plus old x3 minus 8 over 2? Or choice C, new x1 minus new x3 minus 8 over 2? Or choice D, new x1 plus new x3 minus 8 over 2. So that's the first question. And then the second question, this should be B5-2. still dealing with the same system of equations, but now we want to use the Jacobi technique. And again, we're asking, in this case, what will be the update equation for new x2? So we have new x2 equals, again, I'm giving you part of the equation, and then you have the right-hand side of that equation. You have four choices. A is old x1 plus old x3 minus 8 over 2. B is new x1 plus old x3 minus 8 over 2. C is old x1 minus new x3 minus 8 over 2. And D is old x1 plus new x3 minus 8 over 2. And finally, the third question will be in class, but once again, you might as well go ahead and make yourself a note that it will concern this same system of equations. So those are the problems for this lecture on iterative techniques, and that concludes this lecture. So good luck.